Welcome to the e-Pathshala series in computer science. This is the 12th module in the subject of cloud computing. So, in the last class we saw the use of logical clock, Lamport's logical clock and vector clock, and we looked at how these clock values can be used in a distributed environment like cloud to order events. Now, it is very important to correctly order all the events and vector clock and logical clock help us doing that. In this class, we will see what is an election. We will ask why we need election in a environment like cloud, and we will take a look at some good or popular election algorithms. So, first we answer the question, what is an election? This is the definition. When there are many same or similar processes or nodes and one of them is needed to perform some privileged functions, maybe as an example resource allocation, the chosen process or node is called the coordinator, or it is also called the leader, and the method of choosing the coordinator is called an election. So, election is a process of selecting one among many similar or same processes or nodes. So, that is the method of election. So, why we actually worry about election in cloud? Now, if we look at it, the users in a cloud environment have certain expectations. What are their expectations? That the data or computing should be accessed without no latency or at least minimum latency or delay. Data or computing should be resilient without or in spite of all failures that can happen. A failure, a server may fail, there may be power outages, and there may be some natural disaster for which our data centers may be totally destroyed. But irrespective of all such problems, a cloud user expects that access to data and computing should continue. The data or computing should be 100% available to the user, which means that anytime, day or night, the data or computing should be accessible to the user, and no data should be lost or corrupt. So, the value of the data should not change at all at any point in time. So, these are the promises we make to a cloud user, and very important to be able to follow that, because the model is pay as you go. So, therefore, the users are paying for all the services and they expect that we are able to give those services. So, this latency, the data centers or our servers which contains our data or are doing the calculations can be anywhere. User, since they are accessing the data centers over the internet, they can also be anywhere, and the user is not aware of the location of the servers. So, cloud makes it transparent to the users as to where the servers are located. So, all access happens through the networking or the internet, and network is slow and unreliable. So, more time may be taken for a specific communication, and some packets may be dropped which requires to be sent, retransmitted, and this will take a lot of time. So, how do we ensure all these expectations of users, that data should never be lost, data should always be accessible, data should be data or processing should be accessible within a certain period of time? These are all requirements that we need to look at. Now, let us see what is resilience. Resilience is the ability of a cloud based server to withstand certain failures and still continue giving the expected service to the user. And what is availability? Availability is the ability to be up and running in spite of machine failure, network failure, power outages, natural disasters. So, whatever happens, our users will expect that our servers will be available for a reasonably long time, even if I do not say 100%, but at least 99% will be the expectation. So, how the cloud user will behave in case they are not getting access to their data or their computation, it is not an acceptable solution. So, availability or also called reliability refers to making of data, components or any part of the cloud available to the user. In other words, reliability is the outcome and resilience is the way to achieve the outcome. So, how do we achieve all these in cloud? We use the mechanism of replication to achieve all these. So, what is replication? We talked a little bit about replication in our earlier class. The mechanism of making copies of our data is called replication. Similarly, mechanism of copying our processing is also replication, and these copies are called replicas. So, what is the problem of doing replication or what are the problems that can be addressed by replication? Replication makes our data fault tolerant, it keeps the load balanced, it ensures availability and it ensures that data is never lost. So, how do we ensure all these through replication? Basically, we make duplicate copies of our data and processing and store them in different servers. So, therefore, the values or the data are available in different servers. So, what happens if one server fails? We immediately switch to another server. If a part of the network is inaccessible, we look for a server where the network is accessible. If some natural disaster causes a data center to get destroyed, we fall back on other data centers where the same data and computation are replicated. So, replication is a great way to ensure that all the problems or the demands of the users in cloud are maintained. So, these are all our replication requirements. Now, nothing comes for free. So, therefore, replication also comes at a cost. What is the cost of replication? To ensure that all these copies are consistent. What is consistency? If I make some changes in one of the copies, the other copy also should be getting the same updates. We saw in our earlier example how a database in Delhi and a database in South Africa were not appropriate replication because some update came earlier to the Delhi database, whereas other update came earlier to the South African database. So, we are very worried about the consistency of replication. All the clients should see a single consistent copy of data. However many copies we make, if there are multiple users or if the user is accessing multiple locations data, they should all be looking at the same values all the time. The ACID properties of all the transactions should be guaranteed, which means that we have atomicity, consistency, isolation and durability. Any transaction that happens across various servers must have or must possess all these properties to ensure that the transactions are gone properly. So, therefore, the challenge here is that if during a transaction one of the servers break down, we can immediately switch to the other server if and only if we know that all the updates that were happening during a transaction in this server are also reflected in the other server. This is a very serious challenge and a very difficult task to ensure, but that is what replication requires. One specific way of doing this is, do not allow all the copies to do reads and writes. Use a primary copy, keep the replications, ensure that all the updates from the primary copy are sent either continuously or at very short intervals to all the other replications, and ensure that all of them are updated. Even when it is not a primary copy, many times there are, among all these replicated servers, there are certain actions that can be taken only by one specific server. So, when I have many copies of the same process, I need to select one of them to do certain work or to act as a primary. Let us look at some examples. In a cloud based supermarket chain, where the data is made available to all the stores, some information such as additional stock must be only by the accessed by the company head. So, therefore, one of the servers must be having this capability. In another example, we see a cloud based bank. The account information should be stored only in correct in all the servers, and the updates should happen in only one server. In another example, we see that if it is a reservation system, say a railway or an aeroplane or whatever, then different parts will be accessed by different users, but the updates should be continuously sent and received. So, all the replica copies should be updated, and again here certain functions have to be, the aggregation of these different parts have to be done by one of the servers. The point here is, and there are many more examples that we can give. We can see that MongoDB replicates its data and it has a primary copy. Apache Zookeeper also replicates the data and uses one main server to access. So, what is the election? We need a leader or a coordinator among a group of similar processes. If it is a one-time job, then we can fix it and forget about it, but it is not a one-time job. We have to take into account the fact that processes will fail. So, if a coordinator fails, then the system should not stop. What actually is done is, as soon as a coordinator has failed and any one of the participating processes is able to detect that a failure has happened, immediately an election is conducted or held and a new coordinator or leader is selected. So, two phases. The first phase, identify one process which is the leader or coordinator, and then all non-faulty processes are informed about this decision. Whenever a leader crashes, any one of the participating processes will understand that the leader is unresponsive and it will start an election method. Phase 1 and phase 2 will execute. Now, correctness of an election algorithm, there are 2 points. First is the liveness, that means only coordinator should be selected in a finite time. The process of selecting should not go on forever, and the other one is called safety, which says that exactly one non-faulty server will be or process will be selected as the new leader. So, there are various attributes which are used, but the most common attribute is the ID of the process. We see the examples often enough with highest ID, but the lowest ID also is possible. Similarly, IP address, CPU, number of files, disk space, any of these can be the election attribute. So, we will look at 2 election algorithms. The first one we will look at in this module, which is called the Bully algorithm. So, here is the system model for our Bully algorithm. There are n processes. Each of these process has an unique process ID and the system is a synchronous environment. Each process is aware of the process ID of all the other processes in the environment. It is always possible for a process to find out that a process has failed, and this can be done in finite time. We use a reliable multicast communication, which means that message failure is not considered in our election algorithm, and if a non-faulty process receives a message, it necessarily needs to send a reply if a reply is required to be sent. And any process that finds out that a leader has failed starts an election process. So, this is the algorithm. The first step says that PI is the initiator, which means that PI is a process which has discovered that there is a failure of the current leader, and it sends an election PI message to the higher numbered process. Here we are looking at the process ID, and as we said that our assumption is all process knows ID of all other processes. So, it sends an election message with its own ID to only the higher order processes. It sets a time out, that means it sets a clock for T1, and at the end of T1 time an interrupt will be generated. If that happens, that after T1 no response, no reply has come, then it sends a coordinator message to everybody. If it receives even one OK message from one of the election process receivers, then it starts another time interval, timeout interval T2. And even here if a timeout occurs, then what it does is it sends a coordinator, it sends a new election message to all others. That means it starts a new election. Now, when a process receives this election PI message, what it does from a lower priority process it receives, it sends an OK message. So, therefore, as soon as I receive an election message, I send an OK message. Essentially, it tells the other process, I am taking over, you back off. And then it starts an election, which means that it knows the higher order processes in the environment. It will send an election its own process ID and send it to all the higher order processes, and goes back to step 1 and it follows the step 1. So, this is one point that we should look at, that if it has already for some reason started an election process earlier, then it should simply drop the current message. So, here is an example of bully. We have 5 processes, and P95 being the largest process in the environment, largest ID in the environment is the leader. The leader fails, and P20 is the process which detects that leader has failed. So, what it will do? By step 1, it will start a timeout T1 and it will send an election message to the only the higher order processes P30 and P50. It does not send a message to P1, which is lesser number than 20. Both these processes sends an OK message, and P20 starts its next timeout T2. In turn, P30 starts an election message. Higher order processes P95 and P50 have been sent election message, and its timer starts T1, and P50 sends its higher order process P95 an election message, and it starts its timeout T1. Now, remember P20 has the T2 going, that if coordinator message is not received, I have to start another election. P50 sends OK to P30. So, P30 starts its T2 second timeout, but P50 did not receive a OK from anybody because P95 has failed. So, therefore, it continues with timeout T1. Now, at some point in time, since never a OK message will be received by P50, its timeout will expire. So, what will happen when its timeout expires? P50's timeout has expired now, and P50 then realizes that P95 has crashed, and so it sends a coordinator message to all the other processes. And now both this P30 and P20 stops their timeout T2 and accepts P50 to be the coordinator. P50 becomes the coordinator or leader of this environment. So, we look at the correctness criteria. What is our first correctness criteria? Which is liveness, which says that it must elect a coordinator in finite time. So, we assume reliable multicast. So, messages will definitely be received, and we also say that a process has to reply if it is supposed to reply. So, in finite time we can assume that, or we can assure that bully will complete selecting a or electing a coordinator. So, therefore, liveness is guaranteed. What is the safety criteria? Exactly one non-faulty process will be elected as the leader. So, how do we ensure? What happens if two processes, if two coordinators, is there a possibility that two coordinators will be elected? If two processes start the election process, then maybe two coordinators may get elected. So, let us look at an example where we see that both P20 and P30 start the election process and sends the election message to their higher order processes. They will receive the OK messages from the higher order processes. P50 will respond to both 20 and 30, P30 will respond to P20, and P50 will send a message to the lead to the P95, but because bully always upholds the highest ordered process and the process IDs are unique and there can be only one highest order process, therefore, always that particular process will get elected irrespective of however many processes start the election process together. So, therefore, bully upholds the safety criteria also. Now, if we look at the analysis, how do we analyze an algorithm? We analyze an election algorithm and many of our distributed algorithms by counting the number of messages it has to send and receive. It is a very important criteria because we are trying to keep our network uncongested, which means the lesser the number of messages we send and receive due to complete an algorithm, the better the algorithm is. So, therefore, what is the best case? The best case is the least number of messages that are exchanged, and what is the worst case? Worst case obviously will be the largest number of messages. So, in bully, when will the best case occur? When the next largest process finds out. If the next largest process in our earlier example, if P50 finds out that the coordinator has crashed, then the election message is not required because only one higher order process and that has crashed. So, it knows that I am the highest process. So, no election message and no OK message is required, it simply sends the coordinator message. So, this is the best case in case of bully. So, what is the worst case analysis of bully? When do we get the maximum number? Of course, when the smallest process finds out. What will happen? This smallest process has to send 5 or will trigger 5 messages. What are the 5 messages? The smallest ID process will send an election comma P smallest ID to all the higher order processes. Then all the higher order processes will reply with an OK message to this smallest ID process. Then each one of them will start the independent election. So, the second highest ID will send, the third highest ID will send, the fourth highest ID will send, and a timeout T1 for answers at the second highest process will occur, because all the others will receive, as we have seen in our earlier example, all other processes will receive an OK message from the second highest server, but the second highest server without knowing that the highest server is dead, we will send an election message to that and we will never receive an OK. So, therefore, a timeout will occur and then a coordinator message will be sent. So, therefore, these 5 messages will be transmitted for election. So, the best case is when if n is the total number of processes, then it sends n minus 2 coordinator messages. Why n minus 2? Because out of n, one the largest process, which is the coordinator, has already failed and it does not send itself a coordinator. So, n minus 2 messages coordinator messages will be sent. So, worst case, all these 5 messages will be transmitted. So, there are n minus 1 processes altogether and the number of messages, election messages will be sent n minus 1 plus n minus 2 plus n minus 3 up to 1. So, therefore, we get this is an AP series where we say n minus 1, n minus 2, n minus 3 up to 1 and this comes to n minus 1 into n by 2, which is an order of n squared. So, the best case is 1 and worst case is n squared in terms of the number of messages sent and received by the system in Bully algorithm. So, we come to the end of this session. We have seen what is the election, what does an election mean, and then we looked at a few examples where we saw that in an environment like cloud, we very much need something called replication to ensure that all promises to our users are delivered correctly. And in a replicated environment, we saw that one of these must always be chosen for various reasons, either it is because it is a primary copy or it is because it is required to do some special functions. One of these replicated servers or processes should be chosen to do that special work, and that is the process of election. We looked at the correctness of election algorithms. We said that the liveness and safety are 2 criteria using which we ensure that the algorithm is correct. We looked at the Bully algorithm, where we saw that the highest numbered process will always win, and the name has been derived because it looks as if it bullies its way through all the other processes, although the election is started by other processes, but the largest ID process always wins the election process. And we looked at the liveness and safety criteria of Bully algorithm and the complexities with respect to the number of messages. In the next class, we will look at the other election algorithm, which is the ring algorithm, and we will also look at some practical election algorithms that are being used in cloud. These are our references. Thank you.